Hi, I'm Ben-Yaakov. This presentation is entitled BJT Push-Pull Gate Drivers and subtitled When Good Intentions Lead to a Bad Design. In this presentation, I'm going to show a proposed BJT push-pull driver which turns out to be not that good, and so I'm going to explain what's the deficiency of this proposed driver. And then I'm going to go into a little bit more explanation of the classical BJT push-pull driver, and also to show some alternative approaches using MOSFETs and BJTs. So here is the classical push-pull BJT gate driver. This is used when we don't have sufficient current at the source here. So this is sort of a buffer, and in this case we have two transistors, a NPN and PNP, and then there is a network here, the purpose of which is to adjust the current at turn on through R1 and turn off through R2, because usually we like the turn on to be slower than turn off. That is, we would like to have a quick turn off. So this separation allows to adjust the current for turn on and turn off, and the diode is separating between these two. So typically R1 will be of course larger than R2. There are commercial drivers that look like this. That is, they have two outputs so that we can use two resistors for turn on and turn off, and therefore we don't need a diode. So I guess this was an inspiration for a proposed driver based on BJT, in which we are coming off the emitters. There's no connection here in between as before. And of course R1 and R2 will be adjusted as required. So this is the idea of this driver that sort of follows this idea. Like here we have two outputs, two resistors. Unfortunately, this is not a very good idea. In fact, it's a bad idea. And the reason is that in this configuration, we are exposing the base to emitter junction to a reverse voltage which exceeds the maximum permissible value. So let's take an example for the low transistor, for the PNP. Okay? Suppose we are at a situation that the gate has 0 voltage. We turn on here the pulse, so it's becoming 15 volt. So we have 15 volt at the base of this transistor, but since this voltage here, and there is a capacitance here which is keeping the voltage for a while until it's being charged, so this voltage here is still 0 volt. We have 15 at the base. We have 0 here at the emitter, and therefore there is a reverse voltage of 15 volt. However, as it turns out, and this I think is not very well known, the breakdown voltage of base emitter of a BJT transistor is very low, and it is in the range of 6 volt. And here it is. This is an example of a transistor, and we have here the maximum permissible, absolute maximum rating, and the emitter base voltage is only 6 volt. This is the reverse voltage. And here we have, in this example, for a while, 15 volt. So we are here much above the permissible voltage for this junction. To have a better feeling of that, I have here a schematics, LT Spice for simulation. I have the original classical driver. I have here this new driver, proposed driver, coming out of the two emitters, and I'm looking here at the base to emitter voltage, or emitter to base voltage to be more precise, here in the classical one and here. And here is what I get. For the classical one, it's about plus minus 0.6, 0.8 volt. And this is because in the classical approach, the two emitters are together, the two bases are together. So the voltage will be plus minus VBE. That is the maximum voltage between these 2 points. On the other hand, here it could be the full 15 volts. And here is exactly what we see. We see here about minus 13 volt, and here this plus minus VBE as we would expect. Now I don't know how well is this modeled for this operating point. I would suspect that it's not very accurate, because I would suspect that if you expose this junction to a high voltage, it'll break down. So the voltage would be sort of clamped to a certain value and not go to the very high minus values, but I really don't know, and I don't have actual measurements of the circuit, so I cannot tell. Let's have a look now a little bit deeper into the classical driver. One thing that sometimes is missed is the fact that these transistors are not saturated in the extreme voltages. They are not. As it turns out, these transistors are in the linear region for both cases, for the high and the low. And this can be explained as follows. Let's have a look at the lower transistor, at the PNP. Let's assume that the voltage is low, so we are here, and we are now sinking current from the gate. Here it is. And then if I look at the voltage at this point at the emitter, it is the sum of the voltage here plus VBE. Well, even if this voltage is small, because the current is relatively small and the resistor is small, then we still have VBE. So the voltage between the collector and emitter is VBE. That is 0.6, 0.8 volt. And this is quite a bit. For the transistor to get into saturation, both the diodes, base emitter and base collector, are to be in the forward bias region. And this is why we'll get a low voltage, because the two voltages are subtracted. This is not the case here. The base to collector junction is still non-conducting, not in the forward direction. So therefore, this transistor is in the linear region. So therefore, the current of the collector is the current of the base times the large signal gain. So this is the DC current coming here at the steady state. I'm talking about some steady state situation. So this is something to keep in mind. Now, why is this important? It is important because when we operate, say, a half bridge with this driver, and we have a situation that the voltage here is low, so this is supposed to be low, and then we turn on the upper transistor. We have a dVdt here, which causes the current to pass through this gate to drain capacitor, through here, and through here. So what will be the voltage here? At least 2 diodes, okay? At least 2 diodes. And there's some more voltage drops on the resistive part. And this is very bad, because the threshold voltage of modern MOSFET is rather low. It's like 2 volts. And this is already 1.5 volts, so it doesn't take much in order to cause this transistor to start conducting, which you don't want, because it shoots through here. So this is very important. This is why using MOSFET is probably a better choice. In the MOSFET, we have RDS on. So it's not a voltage drop, but it's a voltage drop to a current and a resistance. If the RDS on is low, then for even a fairly high current, the voltage will not go up that much. So the lower the RDS on, the lower will be the voltage as the current is synced during this Miller episode. So this is probably a better way to go, and indeed there are some commercial units like this. Infineon is just one example. There are many other companies. I'll show in a minute another one. So this is the advantage of this, and here you see there are 2 configurations. Here you can put 2 resistors, or here you can put a resistor plus another resistor and a diode, as in the classical driver. Now, there is a problem here. of shoot-through, which in this case you can eliminate by having a dead time between the turn-on of this gate and this gate. But there are some drivers on the market that show this configuration. Well, I don't know if this is the real circuit. Maybe there is a dead time and it's not really the same drive. Maybe it's not. If it's not, then it's very similar to the CMOS logic family, because this is what we have in a CMOS logic family. And indeed, there is a shoot-through, and the energy involved, of course, depends on the transition. If the transition is very fast, then the shoot-through is short and the energy loss is minor. And in this case, you'd expect that the loss will be a function of the switching frequency. The higher the switching frequency, the higher the loss. And in this, if we look at the loss of this particular Micrel, originally now microchip unit, you see that even without load, okay, this is just the unit itself, we see that the drain current is a function of the frequency. It's going up quite a bit. And I suspect that this part of it is due to this shoot-through phenomena. And you see that, say, at 1 megahertz, this is 1 megahertz, it's already like 5 or 6 milliamp as compared to rather low current at a low frequencies, as very similar to the CMOS situation. Now, what about using BJTs in a different configuration? And here is a configuration which is viable and it's not that bad. In this case, we're driving the gate from the collectors, not from the emitters, okay? There is a problem here, and that is that we have a current path like this, and therefore we're going to have current here during the transition when this voltage is in between the VCC and ground. So approximately, this is not exact expression, doesn't take into account the actual midpoint drive voltage. Approximately, the current that you'll have here is large gain, current gain, times the current of the base. Now, this is exactly the current that you would drive the gate with. So it's not much different, it's not a larger current, but still, it's a loss. And of course, it depends on the transition. So this is something to take into account, that if you're going to use a circuit like this, you need very fast transitions here to minimize the losses. Let me wrap up with sort of a funny example, I think. Here is, in one of the forums, a question whether this configuration is good. In this case, we have the emitter here, and this is the configuration. And indeed, very quickly, the guy got an answer that that one will emit fire almost immediately, which is of course correct, because in this configuration, you have a current through this diode, and it goes into the next diode, so the two diodes are shorting the power supply. So this is really bad configuration. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it of interest, and perhaps it will be useful to you in the future. Thank you very much.